Last time, we walked through everything that happens between hitting enter and a web page appearing on your screen, and DNS was the very first system in that chain. This time, we're staying right there, because DNS looks simple from the outside, but underneath that one step is a whole distributed system that somehow still holds up the entire internet. Start with the basic problem DNS solves. Computers don't talk to each other using names. They talk using numeric addresses, called IP addresses, something like 142.250.80.46. That number tells every router between you and the destination exactly where to send your data. Humans are terrible at remembering strings of numbers like that, so DNS exists to let people use names instead, and quietly translate those names into numbers behind the scenes. It's essentially the Internet's phone book, except the phone book is split across millions of servers instead of sitting in one place. Here's why it had to be split up. In the very early Internet, there was actually a single text file that listed every computer's name and address, copied out to every machine on the network. That worked fine when there were a few hundred computers online. It did not work once the Internet started doubling in size every year. DNS was designed specifically to fix that by turning one giant list into a hierarchy, where responsibility for different parts of the namespace gets handed off to different servers. That hierarchy is the part most people never actually see, so let's walk through it using Google.com as the example. Read a domain name from right to left, and you're reading it from the top of the hierarchy down. The rightmost part, .com, is called the top-level domain. Below that comes the actual domain, Google, and everything to the left of that, like www, is a subdomain, another layer of organization the owner of the domain controls themselves. Each layer is handled by a different set of servers, and finding an address means walking down through them one at a time. It starts at the root servers, a small set of servers that don't know where Google.com lives, but do know which servers are responsible for .com addresses and point your query there. Those .com servers are the top-level domain servers, and they still don't know the specific address either. What they know is which server was assigned to handle everything under the .com domain when Google registered it, so they point the query one level deeper, to what's called the authoritative server for Google.com. This is the server that actually has the answer, and it hands that address back up the chain until it reaches you. That's 3 separate lookups just to resolve one name. If your computer had to do that full walk every single time you visited any website, the internet would feel painfully slow. This is where caching becomes the thing that actually makes DNS usable at scale. Caching happens at almost every layer of this process. Your browser keeps its own small cache of recently looked up addresses. If it already has Google.com's address from 10 minutes ago, it just uses that, no lookup required. If the browser doesn't have it, your operating system checks its own separate cache. If that misses too, the request finally goes out to a DNS resolver, usually run by your internet provider or a public service. That resolver keeps a much larger cache shared across every person using it, so if literally anyone else who uses that same resolver looked up Google.com recently, you get an instant answer with no trip to the root servers at all. This is actually why the full 3-step walk down the hierarchy is fairly rare in practice. Popular sites get looked up constantly by millions of people, so their addresses are essentially always sitting in some resolver's cache somewhere. Every one of those cached answers comes with an expiration timer attached, called the time to live, or TTL, usually written in seconds. This number is chosen by whoever manages the domain, and it's a genuine trade-off. A short TTL, say 60 seconds, means if that server's address ever changes, the whole internet finds out and updates within a minute. But it also means resolvers have to re-ask for the address constantly, which is more load on the authoritative servers. A long TTL, something like 24 hours, is much more efficient to cache, but if an address changes, it can take a full day for everyone's cache copies to expire and catch up. Big, stable services usually set a fairly long TTL. Sites that expect to change server addresses more often set it shorter, specifically to keep that flexibility. So to bring it all together, DNS exists because computers need numbers but humans need names. It's built as a hierarchy instead of one giant list, so that responsibility for the Internet's namespace can be split across root, top-level domain, and authoritative servers. And caching at your browser, your operating system, and your resolver is what keeps that hierarchy from being walked every single time, with TTL values controlling how long each cached answer stays trustworthy versus how quickly it can catch up when something changes. Next time, we're going one level deeper into the connection itself, the TCP handshake that happens right after DNS hands back an address. Subscribe if you want that one when it's out.